Everything in Linux network security ultimately flows through iptables. Firewalld, and even Docker's network management all write iptables rules. Understanding iptables lets you see the actual rules in effect, diagnose problems that Firewalld can't explain, and handle advanced scenarios. You won't need to write iptables rules daily, Firewalld handles that. But you need to read and interpret iptables output. When a connection is blocked and you can't figure out why, iptables is where the truth lives. Iptables operates on the concept of tables and chains. There are several tables: filter, nat, mangle, raw, but for basic firewall work, you only need the filter table, which is the default when you don't specify a table. Within the filter table, 3 chains handle different kinds of traffic. Input handles packets destined for the local system, output handles packets originating from the local system, and forward handles packets that are being routed through the system to another destination. The mental model: think of each chain as a list of rules that packets must pass through in order. Each rule either matches or doesn't match. If it matches, the specified action, accept, drop, reject, log, is applied. If it doesn't match, the packet moves to the next rule. If no rule matches, the chain's default policy is applied. Sudo iptables lvn is the command to see all current rules. The L lists rules, V gives verbose output including packet and byte counts, N shows addresses numerically without DNS resolution. The output is organized by chain. Under chain input, you'll see all rules that apply to incoming packets. Under chain output, rules for outgoing packets. Each rule line shows the packet count and byte count, how much traffic matched this rule, the target, what action to take, accept, drop, reject, log, the protocol, TCP, UDP, ICMP, all, the source address, the destination address, and any additional criteria. A typical rule you'd see from Firewalld for allowing HTTP, target accept, protocol TCP, source anywhere, DPT HTTP. This says accept TCP packets from any source to destination port 80. The chain's policy line at the top, chain input, policy accept, means if no rule matches, the default is to accept. Policy drop means if no rule matches, drop the packet. When Firewalld is running, you'll see many automatically generated rules. Lines with accept are allowing traffic. Lines with drop are blocking it. Lines with reject block traffic and send an ICMP rejection back. To see rules in a format you could use in a script, with n-line numbers, iptables L input n-line numbers gives each input chain rule a number, useful for deleting specific rules. Iptables has 4 main tables, each serving a different purpose. For most server firewall work, you only need filter. But understanding the others helps when you encounter unexpected behavior. The filter table, the default, contains the input, output, and forward chains. All basic firewall rules live here. When you run iptables L without specifying a table, you're looking at the filter table. The NAT table handles network address translation. This is where Docker does a lot of its magic, translating container IP addresses to the host IP. Also used for port forwarding, forward traffic arriving on port 80 to port 8080 on the same machine. To view, iptables tnat lvn. The mangle table, for specialized packet alteration. Rarely needed for basic server setup. Used for things like changing TTL or setting packet marks for routing decisions. The raw table, for exempting packets from connection tracking. Very advanced use case. Why does this matter? Docker and some cloud networking tools add rules to the NAT table that can interfere with your firewall. If you've carefully configured Firewalld and traffic is still flowing when it shouldn't be, check the NAT table. Iptables tnat L. Docker adds rules here that pre-accept certain traffic before it reaches your filter rules. The lesson: iptables has more than one table. When debugging unexpected network behavior, check all of them, not just the filter table. Within each table, iptables organizes rules into chains. The filter table's 3 chains correspond to different traffic directions. Input chain processes packets destined for the local machine. An HTTP request arriving from the internet to your Nginx server goes through the input chain. Your firewall rules for allowing web traffic are in this chain. Output chain processes packets generated by the local machine. When your Node.js app makes a request to an external API, the response comes in on input and the request goes out through output. On most servers, output has a permissive default policy: you trust what's leaving your server. Forward chain processes packets that are passing through the machine to another destination. On a server that's acting as a router or gateway, forward matters. On a typical application server, forward has almost no rules and a drop policy. The default policy of a chain is what happens to packets that don't match any rule. Accept means allow everything that doesn't match a rule. Drop means silently discard everything that doesn't match. A common secure configuration: input has a drop policy with explicit accept rules for SSH, HTTP, and HTTPS. This means only the explicitly allowed ports work, everything else is silently dropped. The order of rules matters. iptables processes rules top to bottom and applies the first matching rule. If you have a drop rule for an IP before an accept rule for that same IP on port 80, the drop wins. Firewalld manages rule ordering for you, which is one reason it's preferred for normal management. When Firewalld is running, iptables has dozens of auto-generated rules. This can look overwhelming. Here's how to make sense of it. The top-level chain structure from Firewalld creates its own chains with names like in_public, in_public_allow, in_public_deny. Your traffic gets routed through these chains. For diagnostic purposes, you don't need to understand every chain. Focus on these to see if a port is allowed. iptables in_public_allow, and this chain contains the ports Firewalld has explicitly allowed. You should see rules for SSH, 22, HTTP, 80, HTTPS, 443. To count matched traffic, iptables LVN shows packet and byte counts per rule. A rule with 0 packets was never matched. A rule with millions of packets has been matched frequently. This helps identify which rules are actually processing traffic. To check if a specific port is blocked, iptables ln-igrepo80 shows all rules mentioning port 80. If you see an accept rule, port 80 is allowed. If you see a drop rule, it's blocked. The iptables L output after Firewalld configuration isn't meant to be read directly by humans, it's the serialized version of your Firewalld zone configuration. Read Firewalld configuration through firewall cmd list all. Use iptables L for low-level verification and debugging. Even though Firewalld handles daily rule management, understanding how to write iptables rules directly is valuable for understanding what Firewalld is doing and for debugging. The basic iptables command syntax: sudo iptables, ttable, -a, id, chain criteria j target. A chain, append rule to end of chain. I chain 1, insert rule at position 1, top of chain. D chain rule number, delete rule by line number. Examples: allow SSH on port 22, sudo iptables a input ptcp port 22j accept. Allow HTTP and HTTPS, sudo iptables a input ptcpm multiport ports 80443j accept. Allow loopback, localhost, traffic, sudo iptables a input ilo j accept. The ilo specifies the loopback interface. This rule ensures local services can communicate. Allow established connections, sudo iptables a input m state established, related j accept. This is critical, it allows the responses to connections your server initiated to come back in. Drop everything else, sudo iptables a input j drop. Add this last after all accept rules. Important, direct iptables rules don't persist across reboots unless you save them, sudo iptables save /etc/iptables/rules.v4. Install iptables persistent to auto-restore on boot, sudo apt install iptables persistent. Docker automatically manages iptables rules to handle container networking. This is powerful but can interfere with your firewall configuration in unexpected ways. When you start a Docker container with port mapping docker run p8080:80 myimage, Docker adds iptables rules in the NAT table to forward port 8080 on the host to port 80 in the container. Docker also adds rules in the filter table to allow this traffic. The problem: Docker adds these rules directly to iptables, bypassing Firewalld. Even if you have an open port 8080 in Firewalld, Docker makes port 8080 publicly accessible because it wrote its NAT table rules before Firewalld's rules can block it. This is a significant security concern. Your firewall CMD list all looks clean, but Docker has effectively opened ports that you didn't intend to expose. Mitigation options: Option 1, use Docker's userland proxy, less efficient but respects iptables. Add iptables, false to /etc/docker/daemon.json. This disables Docker's iptables management but requires manual iptables configuration for containers. Option 2, use a private network. Run your containers on a Docker network that doesn't expose ports to the host. Use Nginx on the host to proxy to container ports. Option 3, bind container ports to localhost only, Docker run p127.0.0.1:8080:80 myimage. This makes port 8080 only accessible from localhost, not from external networks. Option 3 is usually the cleanest for a Node.js application behind Nginx. When traffic isn't getting through and you've checked Firewalld, the next step is inspecting iptables directly. Step 1, get a current rule list, sudo iptables lvn line numbers /tmp/iptables current.txt. Save to a file so you can scroll and search. Step 2, look for drop rules, grep drop /tmp/iptables current.txt. Any drop rule that matches traffic you expect to get through is your culprit. Step 3, watch traffic in real time with iptables logging. Add a logging rule before your drop, sudo iptables I input 1j log log prefix input debug, log level 4. This logs all incoming packets to /var/log/kern.log before any other rule processes them. Watch logs, tailf /var/log/kern.log grep input debug. If you see your expected traffic in the logs, it's reaching the server. If not, it's being blocked before iptables. Step 4. Use iptables reset for a clean slate, careful on production. Sudo iptables f flushes all rules. Without firewalld running, this opens all ports. Then reload firewalld, sudo system restart firewalld to reapply your configured rules. Step 5. Check packet counters. After some traffic, sudo iptables lvn shows how many packets matched each rule. A drop rule with increasing packet count is blocking traffic. You found your culprit. Direct iptables rules are lost when the server reboots. If you're using firewalld, this doesn't matter, firewalld restores its rules at startup. But if you've added direct iptables rules for advanced purposes, you need to save them. Check if iptables persistent is installed, dpkgl iptables persistent. If not, install it, sudo apt install iptables persistent. During installation, it asks if you want to save current IPv4 and IPv6 rules, say yes. Save current rules manually, sudo iptables save sudo t/etc/iptables/rules.v4. The iptables save command exports all current rules. Piping to /etc/iptables/rules.v4 saves them in the format that iptables persistent reads on boot. Verify saved rules, cat/etc/iptables/rules.v4. You'll see the iptables rules in a text format. Restore rules manually, sudo iptables restore /etc/iptables/rules.v4. This applies the saved rules immediately. The interaction with firewalld: if you're using firewalld, don't also use iptables persistent for the same rules, they'll conflict. Use one or the other. Firewalld manages its own persistence. For most server setups, use firewalld for everything. Save your firewalld zone config to version control. Only use direct iptables rules and iptables persistent for advanced use cases that firewalld can't handle. A diagnostic question about interpreting iptables output. You run sudo iptables l input vn and see a rule with policy drop at the top, then accept rules for ports 22, 80, and 443, then a reject rule. A request to port 8080 arrives at your server. Jinx is listening on port 8080 for internal testing. What happens to the request? Option A, the request reaches Jinx because Jinx is listening on port 8080. Jinx being installed doesn't override the firewall. The firewall acts before the packet reaches Jinx. Option B, the request is accepted because 8080 is not explicitly listed in any drop rule. This misunderstands how the policy works. The default policy is drop packets that don't match any accept rule are dropped by the policy, not by an explicit drop rule. Option C, the packet is silently dropped by the input chain's policy. Correct. The packet arrives, is checked against rules in order. Does it match port 22 accept? No. Port 80? No. Port 443? No. Reject rule? The reject rule matches everything else, so the packet is rejected with an ICMP message. Option D, the packet is forwarded to the forward chain. The forward chain handles traffic passing through to another destination. A packet destined for port 8080 on this server goes through input. The answer is C. The default drop policy plus the reject catch-all at the end means port 8080 is blocked. To allow it, add an accept rule for port 8080 in firewalld, firewall cmd permanent add port equals 8080/TCP and in firewall cmd reload.